Hi and welcome back. So I think we're live after a break for the month of July. So I myself need to be reminded of where we were. So we're gonna go over the project once again. So as a reminder, so everything's on GitHub, and the project's called Sardine. The links are in the description below, I'll just show it again. I'll just show it. So the link is here. So github.com BigDataBiology-Lab/Sardine. That's Sardine with a Y, because we somehow have a tradition of calling our projects after very old spellings of fish. So we had mackerel, which is a very old spelling of mackerel, and now we have sardine with a Y, which is an old spelling of sardine. Right, so back to, so this is what the code looks like. Sorry, there it is. Make this large, and so the point is to try to look for pseudogenes in bacterial genomes, or apparent pseudogenes but in bacterial genomes, as a marker of genome quality, with the logic being that once we introduce mutations in genomes, what happens is that especially if we introduce indels, that's going to cause genes to break, frame shifts, or introduce early stops, and that will show up as an apparent pseudogene in the genome, but that's not really a pseudogene in the actual physical genome. It's only a pseudogene in the genome that we have sequenced. Right, so what we did so far, and I'm as much reminding myself of what we've done as anything else, is we've worked a lot with simulating data, and so we took some fairly well-studied genomes. So we started with E. coli, we've looked at Bacillus subtilis, we've looked at others like Campylobacter, and what we did is we started by adding mutations. So we start with the reference genome, which we assume to be good, perfect, and then we add mutations, and so we had a very simple model for these mutations, and then as the number of mutations increases, so we can see that the completeness as estimated by CheckM2 goes down. So there's this initial plateau, and then it starts to go down, and the average gene size goes down as well. So this happens in all of these different, I don't know why this one doesn't start at 0, but all of these different, so this is Campylobacter, this is also Campylobacter, okay, I see, this is E. coli, and so if you're paying a lot of very close attention, you can see that the average gene size does go down. That's this sort of orange line, but here in the case of E. coli it starts at 900, so that's in base pairs. So this is also E. coli, so also starts at 900. Campylobacter starts maybe slightly different, but let's see, Bacillus subtilis starts below 900, so that they are not that different, but they are different, and so we cannot use the raw number of base pairs per gene as a metric of quality. That would not be good enough. So the next idea we had was let's look by KO. So we've looked at this. So here we were looking at the average. So this is the length this is the length in the wild type after we have 100 mutations and 1,000 mutations. So 1,000 is probably a good number in terms of something realistic. So and here you can see, so this is the same gene, at least the same KO, and you can see for a number of them they go down. There's quite a drop with 1,000. So this is what we've been looking at. But there's a few where there's actually even an increase, but there's a slight decrease. So we looked at this. All of this was based on simulated data. So we've been looking at this, and we had this. So length by KO, where we loaded all of these results. Okay, so this is what we did the last time. And here at the end, I think we there's a couple. Is this what we did last time? I'm also reminding myself. Okay, yeah, so this is okay, yeah, so we started to get we use this UniRef database. This is actually the same database that CheckM2 uses, so this was partly because in this way we don't need to recompute all of these mappings. We can just reuse them. And then right, this is add. So and then I call this, now we're comparing mandarins to oranges, because we're at least in the citrus family, but it's no longer apples to oranges, but we're still not really comparing like to like. So what we would really like to do is compare something like the GMGC. The reason being that this UniRef 100 KO database, which CheckM2 uses, first of all, it includes partial genes, which the full GMGC also does, but we can select only the complete ones. And second of all, maybe it also includes eukaryotic genes, so it's not really a very good representation. So maybe the GMGC v1 would be the best database for KO sizes. So maybe that's what we. So this, and the other thing I thought about. So I'm trying to remember everything. It's been a month. So the other thing I thought about, which later, is that maybe we should check whether these matches to the KOs happen at the start of the gene. Because that would be more of an indication that we're matching this pattern, whereby we have, the correct start of the gene, and then eventually, a miss, something like a frame shift somewhere, which leads then to the problem. Right. So let me just look a little bit through this. What we had here. So. I'm actually just looking. Let's see. Okay, so here was this length. Okay, so we added this length by KO. Let's just rerun this. So import a bunch of things. Okay, so here we do this thing where we need to import the simulate.py in a special way so that it can load the results into this jug space variable. Here we get, oops, oh, yes, okay. Okay, so tag, okay, let's do just E. coli first. Okay. Sorry, I need to, the camera is slightly in front of that. Just need to move this. Okay. Okay, yeah, this, okay. Okay, so load all of the data. Okay, name the columns. Okay, now. Okay, yep. Yeah, so if you remember, so the query uses this sort of omega symbol as a separator, and then the subject uses the tilde as a separator. So we split by the tilde and the omega. Okay. Okay. Okay, and then we need to find only the cases where there's one-to-one mappings. Okay. Okay, I think it's good, and then yeah, this is what we had. Yes, so you can see. So if we take all of the KOs, we can see that there's basically very little difference. Slight decrease as the number of mutations increases, but then if we link them together, a little bit more. Yeah, a little bit more. Yeah, so you can see especially. Okay, so this is what we did last time. Not bad. Let's do. So let's check the starting position. So let's do these two things today. Number one, we check the starting positions. We do that now, and then we annotate GMGC, which we probably won't be able to finish just because of the difficult or the size of the data set. But that would be that would be the next step. So we can at least write the code, and then I'll run it offline. Actually, let's start even before we do that. Let's start with let's start downloading the code, and then we can figure out whether to run it or not. Downloading the database. So this is the GMGC, Global Microbial Gene Catalog v1. So we can download it. There's other ways to download it, but let's do the global dataset 95 complete genes only, and download selected file. So we could do it this way. Actually, this is not what we're gonna do. What we're gonna do is so this would work. So this is the website. I'll put it in the chat. We could, and here, there's a little, we want everything global, 95%, so unigenes, and we only want the complete genes, basically because otherwise, right? This is the whole reason to use this catalog, is that we want only prokaryotic and complete genes, and we want the nucleotides. Because so it's comparable to the what we have from genomes. So the other way we can do this is getting the it's doing it like this. Is getting it through this git annex And the way I'm actually so get the next. I'm not gonna explain everything now, but it's this utility that lets me get particular files, and in this case I'm actually just gonna use this to get the download URL. So this is the download URL that we want. And so, okay, so download. And I'm just going to switch it to HTTPS. Okay, so I'm going to let this run in the background right now, whilst we look at the other thing. This way, we have this. We'll have this hopefully in half an hour when we're ready to start this. So you can get it through the website gmgc.embl.de. Click on the Downloads tab, select the global 95% complete genes nucleotides. Click the download selected file, and this does this logic for you, or we can go through this gmgc. This is not 10, this is 1.0 data, and then we can select. There's all this subcatalog, and we can select the one we want, which was the 95% nucleotide redundancy complete, and FNA. So FNA for nucleotide .jz. Right, okay, so that's downloading there. In the meanwhile, let's then look. Let's then look here. Okay, maybe we need to go back. Okay, let's do that. Okay, let's do this. We're downloading we're reloading the Okay, I'm not sure exactly what I expected, to be honest. Just do it again. Okay, does this work? Yeah. Okay, so this is the fraction of hits that do not start at the first position. And it goes from or the fraction that do start at the first position. So 94.8 or 94.9 drops to 89, drops to 86, drops to 84. Okay. There's something here, but I'm not sure what. And this was the query start. Okay, let me think of. Let's see the. Start. So this also makes some sense, right? This is actually this is the subject start. So the subject being the KO reference, where we expect. Well, I was actually looking for that this would change. I was expecting that this wouldn't change so much, because we would still be hitting the. Well, I guess we can mess up the start of genes and then have the gene predictor go the other way around. I was expecting that the start of genes would be more or less conserved, and it would be the end of genes that would be messed up. By the way, let's just check how this is going. Okay. So yeah, the file size. Okay, this is. Can just do. It might not finish in time. Yeah, we're. And arguably, okay. Arguably, we want the FNA version. Which is significantly smaller, but still might not finish in time. Let's just do a bit of math in a minute. Okay. So the KO. Okay, let's see. Let's add some notes here. All right, so we are today 0806. Okay, I know it's still 05. I know it's still the 5th in the US if you're watching from the US, but I'm gonna date them according to Australian time. So downloaded database. Okay, I think we might have had some code in the work in progress branch. Yeah, okay. Yeah, we had this, yes, okay. This is, okay, here. No, okay, yeah, this is the work in progress. Okay, okay, so this is what we were. Okay, yeah, so this is what we had. Yeah, so we parsed the KO file and the reference, which is the same reference that checkm2 is using, and then that should have given us the sizes, yeah, sizes of each KO, but unfortunately these are not exactly. These might not be the best references. Okay, we can remove this. So we actually just use this to get the, yeah, we just use this to get the URL. We don't actually use it to download it. Okay. Okay, yeah, perfect. Yeah, exactly. Okay. All right, so it's, yeah, it's been a while, right? Also, some of these, yeah, some of these might not be. Okay, let me. Okay. Yeah, this is not going to finish in time. It's okay. Let's just anyway just look at how we would do it, and then. So what we want to do is we want to do the same thing that checkm2 does. So how can we do that? I'm gonna Okay, so I'm running the checkm2 test thing. Okay, first it runs prodigal. Let's just do a little bit of math here. So we have so 494 minus 431, so that's 63 per minute. And we want to download 13,000 except minutes, so it's gonna take, this is wrong. Yeah, but no, maybe not. Yeah, so this is not gonna finish in time. Okay, but in the meanwhile, let's do this. Diamond black, okay. Okay, so this is what checkm2 is running. So I'm just going to get the first 10,000 genes. So these are sorted, basically so that the shorter genes show up first. So it's not that they are this small. This. Oh. Oh, that's just installed. Diamond sensor. All right. Okay. Yeah, okay. Yeah, so this should work. Obviously, it's gonna take a while. Just check that. Maybe this is not needed. Yeah. Okay, this would work. It would take a while. Maybe now it's going to take a minute or two because we're only using 10,000 genes, and it's the 10,000 shortest ones as opposed to all of the complete genes in the GMGC, which is 95 million or something like that. I think we actually have 95 million. There it is. So this is obviously. Oh, okay, this is not what I expected, to be honest. Does it need? This is not one. Could this be some sort of weird diamond version thing where this is the wrong version of diamond for this database? But at least explain why it runs when, well, the other thing I changed was the number of threads. Interesting. Okay. Something running. Yes, diamond's running. Okay, I'm now guessing this is some sort of, oops. Okay, now I'm guessing that this is some sort of weird, alright, okay, great, this, right, but this would, okay, so this would run, okay, I guess we need to keep the versions consistent, so we can even do it this way, which is great because in this case we wouldn't need to install Diamond separately. It's a little bit, so it's not great that Diamond doesn't auto-detect this and, you know, tell us instead of just crashing. But okay, but we can run it like this. Can run it like this. Wait, that's some, sorry, some sort of error message. Oh, okay, yeah, apparently, yeah, this connection is not great. Okay. Okay, we don't. Okay, we don't, yeah, we don't need to unzip it. Okay, let's have that run there. Okay, so okay, so this is what we, this is what we had. So we had, okay, when we had these percentiles. Okay, alright, and this, okay, this is Diamond now. Okay, so apparently there's some sort of versioning thing where we need to use, so on this database that came with CheckM2, we need to use the version of Diamond that is bundled or downloaded with CheckM2. And so we need to have this on the run. Right, that's fine. Okay, and then we were looking here. Okay, so this is, okay, so these were the percentiles. Let's see. And what we had then. Okay, alright, so this is the drop in percentiles. But this is a little bit fake because this is only the ones where there's a change, I think. Right? Is that true? Yes. Is it? Yes. Yeah, if we do the put that there. Then if we, all of them, yeah. Right, you can eyeball a little change, but it's really hard to see. It's big, yeah. Oh wait, this is the. Okay, sorry, this was this. So if we do this. Okay, can we do this percentile? Okay, this is what I'm doing. Okay. Okay. Right, this again. Yes, okay, this is right. There's a change there. You can see it, right? But you know, it's not that impressive. Goes yeah, this is goes from 0.4, which is so it's not 0.5, which maybe is okay because we would obviously not expect all the you know, maybe some species just have shorter genes on average. That's fine for, or shorter genes for their KO. That's fine. It's a little bit of a shame, but so with 100 mutations we barely see anything, and then with 1,000 mutations we see a difference, but we wouldn't see it. You know, we wouldn't see it. I don't think we would see it across species, because for some other species this one on the left, sorry, the one on the right could be the one on the left, right? It's really hard to assess. Okay, so now what we would need is what we need is to, so if we had the results of running this on the whole data set, on the whole GMGC, we could then do the same plot, and hopefully the plot would look a little bit tighter. So for example here, this is the wild type, so this so I guess in the wild type it's normal that we would in the wild type we would expect things to be the whole range. Yeah, I guess in the wild type we do but then once we have mutations we'd expect some things to be yeah, we'd actually expect an enrichment here. That's rather than a big change in the distribution. Just see what the okay, so yes. So we do something like that. It's a little bit like yeah, it's a little bit like a p-value, right? We expect this to yeah, maybe this is a better yeah, okay. This is a better yeah, I think that yeah, if we think about it as a p-value, but you can do this type of plot, right? Where Yeah, okay. Right, this is yeah, no, this is not the plot I wanted. The plot I wanted was more like this. Yep, let's do 1,000. That's what I want? No, that's not what I want at all. Okay. Yeah, something like this. Right. Yeah, so this bump there, this bump on the, so this overabundance of genes that are much shorter than they should be. This is what we're looking for. Okay. But I'm happy with this. Let's see. We probably need to start wrapping up right now. We are. Where's my clock? That is. And sorry. Yep. We need to start wrapping up right now. The camera is hiding the clock. This, okay, this is much better than before. Okay, you can also see it. So that was the cumulative curve. If we do not the cumulative curve, but the yeah. Okay, the cumulative curve looks a bit nicer. Something like this. Yes, that's correct. yeah, there it is, KO percentiles. Okay, this is not great because this one would actually, okay. Yeah, see this one, even the wild type, it would look like, it could look like it's this looks good. Yeah, okay, Campylobacter might be. Alright, okay, this is what it is. So let's okay. I'm gonna think a bit about this. So we're in the work in progress branch. Yeah. Okay, let me just bit of. Okay, I'm just gonna save this to a temporary file for now. Okay, I'm gonna move this to the main branch. So I'm just moving the commits to the main branch. Okay. All right. Okay. Oh. Okay, we messed this up a bit. let's do. We're gonna do a bit of. Okay. This. We somehow messed that up. Those notes. Okay, so yeah, so here I'm just fixing the Git history, fixing the previous commits, so that's, and now, okay, okay, so we got this. So this is okay. So so this was part of the part of what we fished out of Checkm2 today. So we'll save it for next. Okay, so let's okay, let's clean up a bit. There it is. Be sure. Thing. Alright, let's just push everything. Okay, give me a second actually. I'm gonna do this off screen. Okay. Right, so that's it for today. Yeah, so as usual, everything's online. There's the GitHub, there's a mailing list. I'll be posting a summary later. Yeah, so today we had a lot of just recapping, or I had a lot of just getting my head back into this after basically a whole month without looking at the project. Normally I think I have some memory of what happened the previous week, but it's been a full month, so it was a little bit more hectic than usual. But still, we made a little bit of progress. I think there's some signal here that we can potentially transform into some sort of quality metric, but it's still not clear. And I think this, especially the fact that there's still, how do we distinguish? Will we be able to distinguish things like this, where, Campylobacter jejuni maybe just has short genes? So if Campylobacter jejuni just has short genes, how is that different from, for example, something like the green line here for Listeria, with a bunch of mutations. Could we distinguish these two cases? It's still not clear to me how we can do this. So maybe we'll keep looking at that next week. I think trying to use the GMGC will, especially trying to just use the complete genes, I think will clear a lot of that up. All right, so see you next.